Okay, so I got a polynomial function I want to sketch without a calculator using calculus techniques. So the first thing we want to know is what the first derivative is going to tell us. So I'll change the function notation. So f prime equals 4x cubed minus 12x. Okay. What I want to do is if I want to know where there's potential max and mins, and therefore I can find where my function changes from increasing to decreasing, I got to find what we call critical numbers by setting this first derivative to 0. I can factor that guy. I can factor out a 4x. Set these to 0. I get 4x equals 0. X squared minus 3 equals 0, which gives me a solution at x equals 0. And if I add 3 to both sides, I get x squared equals 3, which means x can be plus or minus root 3. So I'll put those in order. And that's how I'm going to, so those are my critical numbers. That's a negative root 3, 0, and 3. Okay, so what I do, and you'll see this done in a couple different ways, I do this little chart. I break up my real number line by those critical numbers, and then I have intervals from negative 3 to 0. I want to know if it's increasing or decreasing. From 0 to 3, I want to know what's going on. From root 3 to infinity, and then from negative infinity to negative root 3. All right, that's my whole real number line broken up by my critical numbers. Okay, so all you gotta do is pick any test point you want and plug it into your derivative. So what's less than negative root 3? Let's just pick negative 3. If I plug that in my derivative, which is right here, I end up with 4 times negative 3 cubed minus 12 times negative 3. So I just have to decide if that's a positive or negative number. So basically that's going to be negative, right? Because this is negative 27 times 4, so that's over negative 100. I'm just going to add 36 to that. So that's, I don't care what it is. I just care that it's negative. Pick something from this interval. Let's say negative 1. If I plug in negative 1 into here, I get 4, negative 1 cubed, minus 12 times negative 1. That's plus 12. That's only minus 4, so that's positive. Okay, so what this is telling us is something about f. If you want, this is, you can draw a little f prime and f. So if f prime is negative, my function decreases. If f prime is positive, then my function's increasing, right? And the idea is if it's positive for that number, it's going to be the same for anything in this interval, because it could only potentially change at these values where the derivative is 0. Okay, so I'll go, so this video is not super long. I'll just, you can test these if you want. Pick a value from anywhere in here. And this is what should happen. It doesn't always do this, doesn't always alternate, but that's what should happen. So that means I have a, right here at square root of negative 3, I have a minimum value, right? Because it changes from decreasing to increasing. So at negative root 3, we're going to find that y value. I have a min. And then it goes up to 0, and I have a max, a local max, I should say. And then it's going to decrease and bottom out here again when x is root 3, and I'll have another local min. Okay, so the question is, what's the value there? Well, let's do this one. What's the output? It's not that hard to do. F of root 3 is 4, plug into the function, not to the derivative, right? Because now we're looking for a value on the curve itself, so I'm plugging into that function. So it's root 3 to the 4th minus 6x squared, and x, is root 3. So this is root 3 times root 3 times root 2 times root 3, that's 3 squared, that's 9, minus 6, and root 3 squared is 3. So that's 9 minus 18, which is negative 9. So I have a minimum there. And I'll get the same thing here, right? If I make that negative, since these are even powers, it'll come out to the same result. And of course, if I plug in 0 to my function, I get an output of 0. Okay, so I got 3 points on my curve and intervals where my function's increasing, decreasing. What else do I need to know? Concave up, concave down. That means I need the second derivative. F double prime of x is equal to, now the first derivative, let me write down the first derivative, was 4x cubed minus 12x, which means the second derivative is 12x minus 12, or 12 times 12x squared minus 12, or factor out the 12x squared minus 1. If I set this to 0, if I set my second derivative to 0, I have potential inflection points. So set to 0, right? And then that leads me to two solutions, x plus or minus 1. All right, and then I'm going to do the same thing all over again. Break up my real number line, or the domain of my function, in this case, all real numbers. So I have these 3 intervals, and it's the same idea. I'm going to use f double prime to tell me something about f. So f double prime at -2. If I plug in -2 here, I get 4 times 12, which is 48 minus 12, 36. It doesn't matter if it's 36, it matters that it's positive, which means it's concave up. And if I plug in a test value, what's a good test value between -1 and 0? Well, between -1 and 1, probably 0. So if I plug in 0 to here, I get 12 times 0, which is 0 minus 12, -12, which is definitely less than 0. That means it's concave down there. And then if I choose something from here, like let's say 2, if I plug in 2 and I square it, I get 4. I'm going to get the same thing I would if I plugged in a -2, which is a positive result. So the concavity goes back. So that means I have 2 inflection points. When it changes from concave up to concave down, that's an inflection point. When it changes from concave down to concave up, that's an inflection point. So I have 2 of them. They are -1 something and 1 something. So I have to plug in those values to see what I get. That shouldn't be hard. My original function, of course, was x to the 4th minus 6x squared. If you plug in a -1, you get 1 minus 6, -5. If I plug in +1, I get 1 minus 6, -5. Okay. So let's see if I can plot those points and then come up with a graph based on the calculus. So I have -√3 is about 1.7, -1.7, -9. So somewhere around, we'll do our best, somewhere around here. And then I have some symmetry going. We didn't test for symmetry. It would have been helpful, but we'll see. We can kind of see the symmetry here. Those were my 2 mins. So I get a decent graph already. If I decrease to this point and then increase, then decrease and increase. But let's see if we can see those inflection points. -1, -5, and 1, -5. So there's an inflection point and there's an inflection point. What else would be helpful? How about X-Intercepts? Remember that from before calculus? X to the 4th minus 6x squared equals 0. It might help if I just knew where it crossed this, where it crosses the x-axis. I can do a little bit better with my graph, I think. So let's see if we can figure that out. X squared, factor out an x squared. That leaves me with x squared minus 6. And then I get 3 x-intercepts, which makes sense on my graph. X equals 0. X equals plus or minus √6, if you set that one to 0, right? So let's see if that fits with my graph, because the square root of 6 is approximately 2.5, somewhere around here. And of course, we already had this one because it was a maximum. Okay, so let's see. Our graph goes like this. Decreases, bottoms out, increases, tops out, decreases, bottoms out, increases, hits my x-intercept, And there's a couple more things that I could ask you to do. Now you can see the inflection points, right? It changes from concave up, that's concave up, and then the purple is concave down, right? Just on that interval, it's concave down, and it goes back to being concave up over here, right? Concave up. So there's your inflection points. A little harder to see than the max and mins. The max and mins are clear. We call that guy a max. We call this guy a maximum and these guys minimum. So we were right. We could label all those if we want. What did we not do? We didn't check for symmetry. That's an even function. We could have done that. We also didn't look at the end behavior, which we do a lot of the times. I could take the limit f of x as x goes to infinity. And that's pretty clear. Now, I know we're looking at the graph, but it's pretty clear for this function that gets really big, right? That's an even polynomial. So I could have asked you the end behavior before we graphed it. And we should see as x, for this function, as x goes to positive infinity, everything goes up because it's even, positive first term. And then as x goes to negative infinity, everything goes up, right? That's all I'm saying here. And that could have helped us a little bit. But otherwise, that's a polynomial function. Those are the easier ones to graph when I'm doing curve sketching in calculus.